Hello, in this video we're going to be looking at finding derivatives using infinitesimals. Personally, I find this to be a bit more intuitive. It also does not require any knowledge of limits. It also does not require any math besides basic algebra. So first, what is a derivative in case you don't already know? So f of x equals fx squared plus 4x minus 2. This is just a generic function. Um, this function could be anything. This is just a generic function I came up with at random. Um, so if we were to graph it, it looks something like this. This is graphed on a TI-84. So if you were to graph it on TI-84, that's what it would look like. And so the function f of x takes a value. So if we plug in a value of x, it'll return a value of y. And that x value we put in and that y value give us a single point on the graph. So a derivative is a function that's represented. You take the name of the first function, so in this case f of x, and then you just add a little single quote, and you would read that as f prime of x. And so here I drew a line through that point. The f of prime of x, the derivative function, will give us the slope of that line, and so we put in the same x value that we put in originally for the first function, and that gave us the y value. But in the derivative, you put in that x value, and it gives us instead this slope of this line. And so what is that line? Why did I draw a line? You can see I drew a line through the point, but why did I give it that slope? Well, the slope represents the change, how much the function is changing at a given point. So if the x value was much greater, it's if the x value was much greater, if it was up here, we would have a very steep slope because it's changing very fast. But if it was much less and it was down here, we would have we would not have a very steep slope at all. And so first we're going to look at, before we look at how to actually find the derivative, we're going to look at how to estimate a derivative. We're going to estimate the slope of this line. So the slope of a line is simply m equals y1 minus y2, x1 minus x2. So that's the simple equation for a slope you probably learned in high school or even middle school. So first what we do is we look at the x value we put in. So that's the x value we put into the function. That could be anything. Maybe that's around 5, maybe it's 3, maybe it's 2. Doesn't matter. Just you put in an x value into the function, and then what you do is you take two other x values, one to the left and one to the right, and we get two new y values from that. And so y1 and y2, and then we get the slope between those 2 points, not the center point, the slope between the 2 points on the either side, and then we get an estimate of the the um the derivative. But as you can see, it's not exact, it's slightly off. And what I've done here, if you see the purple boxes on the bottom, the amount of space I've put between x1x and x2 is all equal. So I've taken the x value and I've added it to this value d, and then I've subtracted it to the value d. When I take x and I subtract d from it, I get x1. When I take x and I add d to it, I get x2. And so currently d is some arbitrary number, maybe it's like 2 right now. And then what I'm going to do, I'm going to set d equals to d divided by 2. So I'm going to divide d in half. And as you can see, the x1 and x2 get closer to x. And I divided half again, they get even closer to x. But they can never be equal to x, because if they're both equal to x, then we have two equal values. So as you can see, our slope at the top, if we take y1 minus y1, we get 0. And so if both of these values are equal, we're going to get simply 0 over 0, and that's going to give us nothing. And so we're going to look at the infinitesimals. So we know the larger the distance is, the larger the error. So the greater space we have between x1 and x2 is the larger the error. It's more inaccurate the larger d is. But d cannot be 0 because we need two distinct points to calculate the slope. So therefore d must be infinitely small, yet greater than 0. So you can think of this as a number that gets, if you have 0.000000 and the zeros go on forever, and somewhere at the end of that there's a 1, but the zeros go on forever, so you'll never see that 1. It's infinitely small, so it's infinitely small, but it's always greater than 0, so it's never 0. So we're simply going to call this number epsilon, and this will be the infinitesimal. So here we're back to here with the distance, and we're going to say the distance is going to be that infinitesimal. So now we're going to find the derivative equation. So f of x, this was our old function, the same one, and we know the slope of a line is this, y1 minus y2, x1 minus x2. So x1 is going to be x, and we're going to move it to the right by the infinitesimal. And then we're going to, x2 is we're going to take x, and we're going to move it to the left by the infinitesimal. And then we're going to take y1 is going to be, we're going to take the function f of x, but we're going to plug in this new x value. And then the y2, we're going to plug in the new x value. So we're plugging in x1 into y1. So y1 is equal to f of x1, while x2 is equal to f of x2. So then we plug those into our slope, and we get this right here. But if you notice, the bottom can actually be simplified. If we subtract the denominator, you can actually simplify it. So here you take x plus epsilon minus x minus epsilon will become x plus epsilon minus x plus epsilon, which actually simplifies just to 2 epsilon. And so right here is our, this equation right here we can use to derive the derivative for any function. And we're going to show you how to do this in a second. So finding the derivative. So here we have f of x, and then we have that thing right there from last time that tells us our slope. And so here I colored the first one red, and this other f of x minus epsilon and f of x plus epsilon. I gave one red and one blue because we want to find those. These take a little bit of time to find, so we're going to do them both independently. So first we're going to find f of x plus epsilon. So all we're doing is we're taking f of x and we're replacing x with x plus epsilon. So here we have f x plus epsilon squared, 4x plus epsilon minus 2. And then we simply carry out the math and simplify it. And you should end up with something like this. So as you can see, we have f of x squared plus 10x epsilon plus 5 epsilon squared plus 4x plus 4 epsilon minus 2. And all those have different terms, so you can't actually simplify this. So that's simply what our answer will be. That's what f of x plus epsilon is. So now we're going to do the same with f of x minus epsilon. We're just going to plug x minus epsilon into where x is supposed to be, and we're just going to carry out the math to try and simplify this. And as you can see, this is what we get this time. And now what we're going to do is, if you look at the numerator, for m equals, the numerator, the two values actually get subtracted. There's a minus sign between them. And so we're simply going to draw a line under these two, and we're going to subtract them. And as you can see, most things actually cancel out. So all we're really left with is 20x epsilon plus 4 epsilon. So we're going to plug that back into our numerator. We're going to plug that into the numerator, and that gives us 20x epsilon plus 8 epsilon divided by 2 epsilon. And both of those have terms that will cancel with 2 epsilon. And so we actually, once we divide them, we simply get 10x plus 4. And that is actually the derivative. It is f prime x equals 10x plus 4. That is the answer right there. That means if we plug in any x value to this, it'll give us the slope of the line that goes through that point. Now finding the tangent line. The name of that line we're looking for is called the tangent. So it's the tangent line. And so we're going to actually try to practice this by finding a tangent line. So we're going to go back to f of x squared plus 4x minus 2. And this was the derivative we found, f prime x equals 10x plus 4. So find the tangent line when x is 5. And so when x is 5, as you can see, we know where y is going to be. So we have y equals mx plus b. I colored them all. So they're all color coded, so it's easier to follow along. Y equals mx plus b is just the generic formula for a line. So our m is the slope is the same thing as the derivative. So it's f prime of 5. Because 5 is the tangent line we're looking for, tangent line at x equals 5. So we're plugging 5 into the derivative, f of x is at 5, f of prime of 5, that you just take 10x plus 4 and you plug in 5. So 10, 5 plus 4, and that gives us 54. So that 54 is the slope of the line. So now what is y? Well, y, we can get y simply by plugging in 5 into the original function, f of x. So if we plug that in, we get 143. So then what I've done is I've taken y equals mx plus b, and I've plugged in y, I've plugged in m, and I've plugged in x. And the only thing I don't know is b. And so I can actually simply solve for b by subtracting 54 times 5 from 143, and I get negative 127 is b. So now we know b and we know m, so we can conclude that our line, our tangent line, is y equals mx minus 127. And if we actually plug that back into the TI-83 calculator, we actually get this line right there. That line was graphed using the TI-83 calculator. Because that's pretty much the end of the presentation. That's how you can prove derivatives without using limits, simply by using infinitesimals.